Hello everyone. In the third and last part of chapter 3, I'm going to focus on TCP and all the mechanisms that TCP uses for flow control and congestion control and the connection management. And if you basically want to explain why TCP is so great and why TCP is very interesting and many apps use TCP. Let's provide an overview of TCP at the beginning of this lecture. TCP is a point-to-point protocol, which means it has one sender and one receiver, and also it's a reliable protocol, which means you have in-order byte stream plus there would be no data loss experienced by the application layer. And then it is pipelined, which means that it is similar to go back in protocol or uh, selective repeat protocol. And then it is a full duplex protocol, which means we have bidirectional data flow in the same connection, and then it uses maximum segment size quantity in order to specify the size of data that each packet contains. Also, it is connection oriented, which means we have to have a handshaking step at the beginning between two parties, sender and receiver, before any data exchange. And also it has a flow control mechanisms, which means sender cannot overwhelm receiver by sending so many data at the same time and make receivers buffer full. Here is an overview of TCP segment structure. As you see, it is much more complex than what we saw for UDP. We have source port number and destination port number for the purpose of multiplexing and demultiplexing. Also, we have sequence number and acknowledgement number. You have heard of these terms, sequence and acknowledgement, in the previous lecture when we were talking about reliable data transfer. So these are for reliability. We have a receive window size, and then we have a checksum for error detection and some other optional variables that exist in the header of TCP. And obviously we should have some segments for application data. This part is considered the body of the TCP segment, while this part is the header. We have discussed multiple protocols that provide reliability in the fourth layer, in the transport layer in this chapter. If you want to compare TCP to those protocols, TCP is most similar to go back in because it has cumulative acknowledgements. However, it has some differences with go back in. For example, the sequence numbers in TCP is the byte stream number of first byte in segments data. However, in go back in, if you remember, the sequence number counts the number of packets, and in go back in every packet has a different sequence number, but here every byte has a different sequence number. Also, TCP doesn't have any standard for handling out of order segments. It is up to the implementer of TCP what mechanism must be used to handle out of order segments. So here you can see how sequence number and acknowledgement number works. Let's assume we have two parties, host A and host B, So host A can be sender and receiver. Host B can also be sender and receiver, because TCP, as we said, is a bidirectional protocol. So assuming that host A sends data with 1 byte, like character C, to host B, it sends it with a sequence number, for example 42, and acknowledgement number 79. Then host B, if host B receives this data successfully, it has to it has to set the acknowledgement equal to 43, which is 42 plus 1. So the acknowledgement of the response should be the sequence number plus 1, and it sends its own sequence number, which is 79. And let's assume that host B simply echoes back the data that it receives from A, so it again resends data C back to host A. So as you see, the data has only 1 byte. That's why we only increment numbers by 1. And then after host A receives the host B's response, it replies by sending sequence number 43 and acknowledgement 80. So why acknowledgement 80? Because in the B's response we had sequence number equal to 79. Now acknowledgement has to be the next byte that host A expect to receive from host B, which is number 80. So always remember, the acknowledgement number is the sequence number of the next byte that you expect from the other side. As you remember, in the pipeline protocols that we saw before, like GBN and selective repeat, we had a timeout value. Now the question is how to set timeout value for TCP, which is a pipeline protocol. Obviously, it has to be longer than an RTT, but what is RTT? RTT varies in different times depending on the status of the network. If you consider timeout too short, then it will cause some premature timeout and unnecessary retransmissions of data, and obviously it decreases the throughput of network. Also, if you consider timeouts too long, again, you would have very slow reaction to segment loss, and that also results in the same very low throughput of the network. So setting timeout too short or too long will cause some efficiency problems. Therefore, we have to find the best value for the timeout. To find the best value for the timeout, we have to be able to estimate the right RTT. If you consider sample RTT equal to the time it takes for an ACK to be received since the segment is transmitted, then we can find a good estimation for RTT by finding the average of several recent measurements of sample RTTs. In order to find a smooth estimation of RTT, we need to use a formula like this. This formula provides a smooth estimation of RTT. Basically, it is the weighted average of the current value, the most recent RTT value, and the historical value for RTT based on the last, for example, 10 experiments that we had for finding the sample RTT. So This formula has a memory, which is the history of sample RTTs, and the most recent one, the current one. So the alpha value specifies how we can handle the weighted average. If you set alpha equal to a larger number, it means that you want to increase the impact of the most recent value. If you if you decrease the value of alpha, it means that you want to emphasize on the historical value of the estimated RTT, and you're not very interested in the current value, so you don't want the current value affect your estimated RTT a lot. And if you set alpha very low, then you would have a very smooth curve, as you see here, over time. But if you set alpha into a higher number, then you would have less smooth curve. In this plot, you see the difference between the estimated RTT and sample RTT. As you see, sample RTT may increase and decrease a lot, but the estimated RTT has a very smooth trend. After estimating RTT, the value of timeout, the timeout interval, is calculated by adding the estimated RTT with 4 times some safety margin, which we call it DEV RTT, the deviation of RTT. This DEV RTT is calculated in this formula. This formula basically finds the weighted average of deviation that RTT has, the sample RTT has from the estimated RTT. So you can take a look at these two equations to see how timeout interval is related to the estimated RTT. Obviously, timeout interval must be greater than estimated RTT, otherwise we would have a lot of premature timeouts. A very interesting mechanism that TCP uses to improve its efficiency is called TCP fast retransmit. Usually when we reach to a timeout, we figure out that a segment has been lost in the network, but waiting till the end of timeout period is a very slow process, and you have to wait a lot before resending the lost packet. There are some other ways that we can find signs of lost segments. For example, if you receive a lot of duplicate acknowledgements for the same data, then you should be suspicious that your data has been lost in the network, even if we have not yet reached the timeout period. So you don't need to wait till the end of timeout period before retransmitting data. You can simply retransmit data if you receive a lot of duplicate ACKS for the same data. So here is the rule. If sender receives 3 acknowledgements for the same data, which we call a triple duplicate acknowledgements, then it sends the unacknowledgement segment with the smallest sequence number. It's likely that unacknowledgement segment has been lost, so that we don't need to wait for timeout. Why it's likely that the unacknowledgement segment is lost? Because we are receiving the same acknowledgement 3 times, so that means something is wrong. In the next slide, I'll explain more about a scenario that we receive 3 acknowledgements for the same data. In this scenario, host A sends 8 bytes of data to host B at the beginning with sequence number 92, and obviously host B has to reply with acknowledgement 100 because 92 plus 8 is 100, right? And after sending those 8 bytes, then host A continues sending more data. For example, with sequence number 100, it sends 20 bytes of data, and then it continues sending 3 other segments. This is another one, another one, another one. So it sends a total of 5 different segments. The first one had 8 bytes, the second one had 20 bytes, and then it sends 3 more segments, but the second segment will be lost at the middle of the way. So host B, the only thing that host B is received is the first one, the third one, the fourth one, and the fifth one. So it still waits for acknowledgement 100. So it doesn't matter how many of them it receives, it again asks for acknowledgement 100. Why? Because because 100 is the smallest sequence number of the byte that host B has not yet received. Therefore, it keeps sending the acknowledgement 100 to host A. So host A has 2 options. It can wait until the timeout, which is this long, reaches, or it can retransmit data before the timeout. Why host A has the second option of retransmitting before the timeout? Because it receives multiple acknowledgements for 100, so it can be suspicious that this 20 bytes of data has been lost at the middle of the way, so it has to retransmit that data again. Next, I will talk about the flow control mechanism that TCP provides. Here is the schematic view of different layers in the receiving side. In the 5th layer, we have application process. In the 4th layer, we have TCP code, and in the 3rd layer, we have IP code, where IP is a protocol for the 3rd layer of the network. So, as we saw before, between the 4th and 5th layer, we have a socket. So here we have TCP socket, and the socket has in the receiving side has some buffer. So this buffer will store information as they are received from the 4th layer, and then it simply delivers those data to the application process. There may be some cases in which the rate that TCP adds data to the socket buffer is way more than the rate that the application process removes data from the TCP socket buffer. Therefore, the buffer may become full. If the buffer becomes full, then we have some data loss. So that's why flow control is an important mechanism that TCP must have. So in the flow control, receiver controls senders, so sender won't overflow the receiver's buffer by transmitting too much data in a too fast rate. In order to implement the flow control, TCP receiving side advertises the free buffer space that it has to the sending side, so that the sender knows how much free space receiver has in its buffer, so that it doesn't send more than the free buffer space in the receiving side. So this way we can guarantee that receiver will not have a full buffer, or otherwise, or in other words, we can guarantee that the receiving side buffer will not overflow. TCP has a state variable called RWND, which means receiving window, which shows the free buffer space, and always receiver advertises this value in TCP header, so that the sender understands the limit of data that it can send to the receiver. Basically, sender limits amount of unacknowledged data to receiver's RWND value. Next, we talk about the connection management in TCP. Every TCP connection has a number of parameters, for example RWND, that both sides have to agree on them. So before exchanging data, sender and receiver must handshake so that they can agree to establish a connection and agree on the connection parameters. In order to agree to establish a connection, two parties may have a two-way handshake. In the first step, one party requests a connection with a certain parameters like X, and then the other party simply accepts the connection, and after they accept the connection, they both consider the connection as established. But this two-way handshake solution doesn't work all the time because of message loss and because of message reordering. In the next slide, we will see why two-way handshake doesn't work. Here is a simple scenario in which two-way handshakes fails. Look at the left-hand side scenario. First, the first party chooses X, which is the parameters for the connection, and requests connection with parameters X. The other side, when it receives the request, it accepts with those parameters X, but this message will arrive very late, so the first party thinks that its request has been lost at the middle of the way, so it retransmits the request connection again, and before the second request connection is received by the server, the client terminates and server forgets X, but after the server gets the request again from the client, we would have a half open connection because client has already terminated, but server thinks that this is a new connection, so it establishes the connection again. So having a half open connection is obviously no good. So two-way handshake doesn't work properly. You can check the second scenario in which two-way handshake fails. So since the two-way handshake doesn't work, TCP uses a three-way handshake. In the three-way handshake, the client and server state, they both have three different states. Client has listen, SYN message or synchronization message sent, and established. Server, on the other hand, has listen state, synchronization received, SYN received, and established. First thing is done by the client when it chooses the initial sequence number X, for example, and sends the TCP SYN message. That's a special message, synchronization message. There's a SYN bit in the header that you have to set it as 1, so that it means that that message is a SYN message. Then when the server receives the SYN message, it chooses its own sequence number, which is Y, and sends this TCP SYN ACK message. So SYN message is sent by the client, SYN ACK message is sent by is replied is sent by the server in response to the SYN message of the client. And after this point, the server is in the SYN receive state and client is in the SYN sent state. But when the server's response is received by the client goes to the established state, which means that it considers the connection as established, and then it replies back by the acknowledgement number of y plus 1. What was y? Y was the initial sequence number of the server, so it sends the acknowledgement of y plus 1, which means it expects y plus 1 from the server. So when the server receives the acknowledgement of y plus 1, it finds out that the client is alive, and it also goes to the established state. Next, we talk about the principles of congestion control. So congestion means when too many senders, too many sources send too much data too fast for a network to handle. Obviously, it's different from flow control. In flow control, we had the receiving side that had a receiving side which couldn't afford receiving a lot of data. But here, in the network congestion, network cannot handle that much of data. Not necessarily a single host. Network congestion has a number of manifestations. For example, when you see a lot of lost packets or long delays for long queuing delays in routers, these are some signs of network congestion. Let's consider a simple scenario in which we have two senders. This is host A and host B. They are both sending data toward these receivers, and we have one router at the middle of the way with infinite buffer. So this is not a reasonable assumption, but this is just an assumption. And then the output link capacity of the output link that the router is connected to is R, and we don't have any retransmission. The assumption is we have no retransmission. Again, this assumption is also not realistic. Also, we have two variables. One is a lambda in, which shows the rate of incoming data flow to the router, and we have a lambda out, which is the rate of outgoing data flow. So in this scenario, you can consider a lambda in as the rate that original data is sent, and lambda out as the throughput that these receiving sides will experience. Since we have two connections and the output link capacity is R, so per connection throughput should be R divided by 2. In this case, R is assumed to be the bottleneck of the connection, so the maximum per connection throughput is equal to R divided by 2. So since we assume that the buffer capacity, the router's buffer capacity is infinite, while if we increase lambda in, lambda out is first increased linearly, but finally it remains constant, because after some point you cannot send more data through this link. So this link will be saturated and it cannot handle more than r divided by 2 transmission rate. So the lambda out will remain constant after we increase lambda in more than r divided by 2. Also here you see the plot of delay uh, when lambda in increases. So when arrival rate increases in this scenario, although the buffer is unlimited, but the delay will grow exponentially. Why? Because every packet will see more queuing delay, because we are growing the size of elements in the queue. Therefore, every packet has to wait more and more and more in the queue before sending out through the outgoing link. So the delay will exponentially increases as we approach the arrival rate toward r divided by 2. Now if you assume that we have a finite buffer in the router, which is the much more reasonable assumption, then we should have some retransmissions, because a lot of packet loss may happen because of buffer overflow. Therefore, assuming that in the application layer input is equal to output, which means lambda in is equal to lambda out, this is not the case when we talk about transport layer, because in the transport layer, the real lambda in, which we call it lambda prime of in, is equal to lambda in plus those retransmitted data. Therefore, lambda prime of in, which is the arrival rate in the transport layer, is greater than the arrival rate in the application layer. So since lambda in was equal to lambda out, now lambda prime of in is greater than or equal to lambda out. So in this situation, if if we think the ideal scenario, in the ideal scenario, the sender knows when router buffer has empty space, and on that moment it sends data. It's a very unrealistic assumption, but that's the ideal case in which the sender has perfect knowledge. In that case, we would have this plot in which lambda out increases linearly as lambda in grows. As another idealization assumption, we assume that sender only resends data and retransmit data if it knows that the packets are lost by the router. Under these relaxing assumptions, we would have the following plot, in which lambda out will not reach to r divided by 2 when lambda in reaches to r divided by 2, because we have to consider some incoming flow for the retransmitted data. And if we become even more realistic and we assume that the sender sends 2 copies prematurely, if even if the packets are not dropped by the router, then the slope of this curve would be even lower, and lambda out would not be that much as we reach to r divided by 2. So here we may have the lambda out equal to 80% of lambda in when the lambda in reaches to its max r divided by 2 transmission rate. So as you see in this scenario, the cost of congestion is to do extra work and to do unneeded retransmissions. In the case that we have more than two senders, multiple senders, then we would have a more severe cost for congestion. And when you increase the lambda in, you may the throughput may converge to zero. In fact, when packets are dropped, any upstream transmission capacity used for those drop packets has been wasted. So this is the curve that is the most realistic one. As you see, lambda out increases as lambda in increases up to some point. This is the maximum value for lambda out. After that point, it decreases tremendously. Why? Because after some point you have a lot of retransmissions and data loss and packet loss that basically the throughput would be almost zero. So the throughput converges to zero after some point. Now, in order to handle network congestion and control congestion, there are two different approaches. One is end-to-end congestion control. The other is network-assisted congestion control. In the end-to-end congestion control, we have no explicit feedback from network. But in fact, network core doesn't help us to understand whether congestion happens or not. Congestion is inferred from the end systems. For example, when you have a lot of loss or delay, the end system will figure out that the network is congested. However, in the network assisted congestion control, routers provide feedback to end systems. So since we are focusing on TCP, we do not talk about network assisted congestion control. We focus on the end-to-end congestion control. So next I'm going to talk about TCP congestion control. TCP has a state variable called CWND. CWND stands for congestion window. It is basically equal to the window size of TCP. So CWND specifies how much transmission rate can be, how much window size can be, and so for TCP to handle congestion and network congestion, it has to increase the window size and CWND gradually until a loss occurs. We call it additive increase. It increases CWND by one maximum segment size, which we call it MSS, maximum segment size, which is the unit of measurement of data that is sent by TCP protocol. So we increase CWND congestion window gradually in a linear manner until a loss is detected. So the CWND's slope is one maximum segment size per RTT, and then as soon as a loss happens, we have to cut CWND in half. So it has a multiplicative decrease, but it has an additive increase. In other words, you can say it has a linear increase, but it has an exponential decrease. We cut it in half. So here is the plot for CWND for the window size as we go over time. So the horizontal axis is time, the vertical axis is the size of congestion window. So we start from some point and we gradually increase the size of congestion window with a constant slope, and then a loss happens here. Therefore, you have to cut CWND in half, so it comes here, and then again it gradually increases until the next loss happens. So you have to cut it in half again, and then we gradually increase until a loss happens here. Then we cut in half again, same story. So in this plot, how many losses have happened? 1, 2, 3, 4, 5. So 5 losses happened in this plot. So again, CWND specifies the window size, which means that the last byte sent has a index. If you write the last byte sent minus the last byte acknowledged, that value should be less than or equal to the CWND. So the number of bytes in flight has to be less than or equal to the congestion window size. Also, CWND is dynamic, as is a function of perceived network congestion. As you saw, we had additive increase and multiplicative decrease. So it's a function of time. It depends on different states of the network. If the network is congested, you have to decrease the CWND. If the network is not congested, you can gradually increase CWND. This is how TCP congestion control works. So this TCP sending rate is roughly equal to the CWND, the congestion window size, divided by RTT. But since CWND is not constant, therefore the rate of sending data by TCP is also not constant. We can have an average value for the rate. When the connection begins, the rate has to be increased exponentially until the first loss happens. So this TCP Slow Start is different from additive increase that we talked about it before. Here we are talking about the beginning of the connection. Initially, CWND is set to be 1 MSS, which is a very small value, but you have to double the CWND every RTT until a loss happens. So for example, at the beginning we start with sending one segment. After the RTT, after the first RTT, we double the number of segments. So the next we send 2 segments. After we receive the acknowledgement for each of those segments, we double the number of the number of segments that we send. So this time we send 4 segments, and then we do this. We increase it exponentially until a loss event happens. So although the initial rate is slow, but it ramps up exponentially fast. So as I said before, there are 2 indications of a loss. One indication of loss is that we reach to a timeout. This is a more severe indication of loss, and that's a sign of severe network congestion. Since it is a sign of a severe network congestion, you have to set CWND to 1 MSS. So you have to bring the CWND all the way to 1 MSS. However, if the loss is indicated by 3 duplicates of 3 duplicate acknowledgements, for example, if we receive 4 acknowledgements with the same acknowledgement number 100, the one that we saw before, then it means that the network is not that congested. Why? Because the network is still capable of delivering some segments, although the segments are acknowledgements. So we don't need to set CWND to 1 because it's not that the network congestion is not that severe. So we basically cut the CWND in half, and then we grow it linearly again. So there are two versions of TCP. One is TCP Reno, the one that I just mentioned, but TCP Tahoe always sets CWND to 1, whether the loss is indicated by a timeout or it's indicated by 3 duplicate acknowledgements. Here is the plot of congestion window over time. As you see, we have an exponential slow start step. This is the slow start in which we double the window size at the beginning until we reaches to the variable SS threshold. SS threshold is the slow start threshold. S means slow. The second S means start. Slow start threshold. So after we reach to this point, to a slow start threshold, then we increase the congestion window linearly until the first loss happens. After the first loss happens, for example, this loss is the severe loss, which means this happens by timeout. We have to go all the way down to 1. Or if it happens by 3 duplicate acknowledgements, we have to go to the we have to set the congestion window to half of its current value. So it was 12. Now we have to cut it into 6. So this black plot shows the case that TCP Reno reset the cuts the window size in half when three duplicate acknowledgement is received by the end system, and then after this point we gradually increase the window size. However, in the case that we set the congestion window to 1 after the loss, we have to do another slow start until the slow start threshold. So this line would be exponential, and then after that we should have a linear plot. So in this FSM you can see details of TCP congestion control mechanism. There are 3 states. One is a slow start in which we have to exponentially grow the congestion window size, or in this we have another state which we call it congestion avoidance. In this state we have to increment the CWND gradually. We have to increment it by MSS every 1 RTT, and then we have a fast recovery in which in the case that an error, a data loss happens, we have to either set the CWND to 1 or we have to cut it in half. Although the TCP throughput is a function of window size and it's not constant, but we can have an estimation for average TCP throughput since this plot is an approximation of the plot of C congestion window size. We can estimate the average TCP throughput as 3 divided by 4 times the window size divided by RTT. The window size W is the window size when loss occurs. So again, that W is not constant, but assuming that that W is constant, which means the window size in which for which a loss occurs is always a constant value equal to W, then we would have a simplified plot like this, and the average TCP throughput can be estimated as 3 divided by 4 times W divided by RTT. The logic behind this formula is this line is which is in 3W divided by 4 y. So the y here is equal to 3W divided by 4. This line is an estimation of this zigzag plot. There is even a more complicated estimation for TCP throughput, which is dependent on L, where L is the segment loss probability. You really don't need to know the logic behind it. All you need to do is you may learn it for yourself. I don't ask any question in the exam regarding this formula because it's not easy to remember. We introduce another feature of TCP. TCP is fair, which means that if k TCP sessions share the same bottleneck link with bandwidth R, each of those sessions should have the average rate of R divided by K. So when you have two TCP connections going through the same link with the same bottleneck link with capacity R, each one of them should enjoy the capacity of R divided by 2. If one connection uses more than R divided by 2, that's not fair, but TCP is set up in a way that it satisfies fairness.